Let's have a look at our little mini assignment that we handed in on Friday in preparation for our test coming up on Wednesday for you guys. We start off this assignment with a question that we're not used to seeing. Okay, this is different than a question that we've seen before. You know what? On June 25th, and you guys write your diploma exam, you're probably going to see questions that are different than we're used to seeing. Okay, that's one thing that I can say about these people that write the exams. They're good at coming up with unique things. Still, after how many dozens and dozens of exams that they've made up, they're still good at coming up with questions that are unlike stuff you've seen before. Now, having said that, a lot of the questions are going to be much like questions you've seen before, but you'll see something, kind of like question number one, that's different than what we've seen before. That's okay. Doesn't mean we can't handle it. Okay, we've seen the concepts before. We just haven't seen the questions before. If you look at the diagram and the information that goes with the question on page one, this is a current balance apparatus. This is not unlike the lab that you guys did last week and handed in on Friday. Now, the way that it's set up is a little bit different. Okay, we got the C-shaped magnet kind of above the wire instead of below the wire, and little differences here and there. Got an ammeter and so on. We had a different way of measuring current. But in the end, it boils down to the same thing. Having said that, we're not asked to find in this question what we were asked to find in your lab. In your lab, you had to find the magnetic field strength by changing the length of wire and by changing the electric current. Here in this question, they're giving us all kinds of different research questions. Basically, we had two. We had, the first one was, okay, let's change the length of the wire and see how we can get magnetic field from that. Let's change the current and see how we can get magnetic field from that. Here, there's 5 research questions. And then they give me 4 variables. And the question says, pick a research question. Pick one of the 5. It doesn't matter which one. Pick one of the 5 and then identify the variables that go along with that research question. Okay, this is a question, even though we've never done it in the context of a test before, we do this when we do labs, right? We identify what we're manipulating, what we're responding, and so on. In my estimation, when I went through and made the answer key up for this, I found 10 different answers. 10 different answers that we could accept for that. Okay, I'm not going to go through all 10 solutions. I'll go through 2 or 3 solutions, 2 or 3 possibilities, and then we'll give you the other 7 or 8 answers, just in case you pick something else. But in the end, if we go through kind of a reasoning for first 2 or 3, then we're probably going to be in decent enough shape. Here's what I want to do first. Hey, I want to pick research question number 1. Okay, research question number 1, right, which is very much actually like the lab that we did last week and headed in on Friday. Does the length of the wire in the magnetic field affect magnetic force? What's our research question? Well, it's number 1. What's our manipulated variable? What's our manipulated variable? Does the length of the wire in the magnetic field affect magnetic force? What are we changing here? What did we change in the lab that you guys handed in on Friday? The length of the wire. So it's got to be, the manipulated variable has to be 7. If you picked research question number 1, the next possibility has to be 7. Now the responding variable, well, it's got to be the same as well. You got no option here. If you picked research question number 1, the responding variable has to be the magnetic force. That's what changes in response to you changing the length of the wire. So it's going to be 176. Now, here's where you could have a couple possibilities. One of the variables that must be held constant. In other words, one of the control variables. Well, if we're changing the wire length, then that's not going to be held constant. If the magnetic force responds to that, then that's not going to be held constant. What else has to remain constant? Well, you could have 8, 1, 7, 6, 8, because you got to keep the strength of the magnetic field constant, but you got to keep the current constant as well, right? Everything else constant. So it would be 1768 or 1769. Both of those would work. Let's pick research question number 2. Again, we're going to go through the same thought process here. The research question number 2, our manipulated variable here is the current this time. Does the magnitude of the current affect something? So we're going to say 9 goes with 2. Does it affect the magnetic force? That's what responds to the current. That's what changes because of the current. So that's going to be 6. the responding variable. 296, what has to be held constant? Well, you got to keep the length of the wire constant. 2967, or, well, we also have to keep the magnetic field constant, so it could be an 8. 2967, 2968. Okay, let me read you the other 6 combinations that I came up with as being possible answers. And if anybody has a question about a particular one of those answers, then just raise your hand and we'll go over it. Otherwise, we'll move on. I got 3867, 3869. I got 4967, 4968. And I got 5768 and 5769. All right. I had people all over the place. You guys did a great job, by the way, on this question. Okay, you nailed it. Okay, but I had people all over the place in terms of which research question they picked. That's fine. Hey, that's fine. Pick whichever one you want. Identify the variables that go along with it. You guys did a good job no matter which one you picked. Personally, I think the first 2 made the most sense to pick because we did a lab that essentially had those 2 research questions, almost those 2 research questions, right? Now, having said that, hey, there's going to be people in the province, when this appeared on a diploma exam, there's going to be people in the province that hadn't done this lab. Okay? That could happen to us, right? We could have a question on an exam that has a description of a lab that we haven't done. Okay? If you remembered, variables and so on, that's great. If you didn't, okay, it's okay. Just make sure you're able to figure it out, what the variables are that go along with it, all right? In that event that we see an experiment that we've never done before, that's okay, just work through it. So our first question, 2 pages long, is done. Well, it wasn't too bad of a question. Then we have our first multiple choice question, which is a little bit trickier. Maybe not a good way to start off multiple choice questions with a challenging one like this. Here we have a magnet that we're moving downwards, and maybe it's moving because of gravity. It looks like it is actually. It's dropped onto a foam block, so it's moving downward because of gravity. And right now, before it reaches before it reaches the copper ring, it's accelerating downward at 9.81 meters per second squared. As it enters the copper ring, it's actually not going to accelerate at that rate. Remember on Thursday, for those of you who were here on Thursday, we learned about Lenz's law. We also learned about electromagnetic induction. 2 things that we did on Thursday. Let's actually go back, even further back than that. Way back early in the unit, we learned about a discovery made by Ørsted almost 200 years ago in 1819. That discovery was electricity generates magnetism. Okay, electric current makes a magnetic field. Then on Thursday, we learned about a discovery made by Faraday, made by Henry, independent of one another, that said kind of the opposite. Magnetic field makes an electric current. Now, in order for that second thing to happen, for the magnetic field to make a current, one of 2 conditions had to be met. You either had to have, you got a wire, you got a magnetic field, you either had to move one of them, move the wire or the magnetic field, or you had to change the strength of the magnetic field. One of the 2. But the bottom line is, you got a magnetic field, you can make a current. Now, on Thursday, the second thing that we learned, which is kind of the third thing that I want to talk about here, is Lenz's law. Basically, Lenz's law says, look, you got a magnet and you got a conductor and you move one of them, you're going to generate an electric current. Okay, that's principle number 2 here, right? The principle that we have identified up here. This is the Faraday electromagnetic induction that we learned about on Thursday. You got a magnet, you got a conductor right here, which is the copper ring. You move one of them, you're going to generate a current in that copper ring. But that copper ring will generate a magnetic field, okay? Because that's what we learned way back at the beginning of the unit. Electric current generates a magnetic field. That was the first principle that we learned in the unit. Okay. First thing, 1819, electric current generates a magnetic field. But now we got 2 magnetic fields. We got the first one, and we got the second one. The first one being this one right here. The second one being the magnetic field that was generated by the current in this copper ring. those two magnetic fields do what? What's the big deal with those two magnetic fields? The one that we made and the one that we already had. What's the word I'm looking for? It starts with a vowel. They will always oppose each other. Okay, they'll always oppose each other. So that means right now, nothing's in this copper ring. But as I drop this magnet towards the copper ring and through this copper ring, you're going to generate a current in the copper ring, right? Magnetic field generates an electric current. Which way is that current going to go? Don't know yet. But I do know that current that's generated in the copper ring will generate another magnetic field. So that not only do we have a magnet being dropped, we have a copper ring that's become magnetized as well with a certain polarity, north and south. Okay, what do we know about the magnetic field that we just made? Let's draw a little pretend magnet inside there. There's not really a magnet there, right? But we're producing a magnetic field here, so let's pretend there is a magnet there. What's the polarity of it going to be? Which end does this have to be, north or south? Forget about a hand rule, forget about any of that stuff. We know that this end has to be what, Parker? Has to be south, because it has to oppose the motion of the original magnet. Got it? So this end's going to be north, this end's going to be south. All right, let's go back to the coil rule that we learned earlier on in this unit. The coil rule says, if we've got a coil or even just a ring of copper, and you have a magnetic field that's generated in that points from south to north inside, okay, if my magnetic field goes this way, from south to north inside, then I'm going to stick my thumb downward in the direction of that magnetic field. My fingers are going to point in front of the copper ring or in front of the coil towards the right. So that means the current is going to point towards the right in the front, and then in the back it's going to point towards the left. That means, if we look at our possibilities here, the electrons inside the copper ring will move from Y around to X. So that's going to leave me with C or D as my options here. Then the only question is, at point Y, we're going to have what? Is Y going to be negative or positive? Well, if the electrons are leaving Y and going towards X, then Y is going to be positive, right? We're losing negatives. We're losing electrons. It's got to be positive. So the answer is going to be D, right? Okay, that's a good question. Okay, sometimes I pick questions on these little assignments that I don't necessarily like them. I just think they're good to go through with you. I actually like this question. I think it's a challenging question, but I think it's a good question. There is, on your exam tomorrow, for you guys it's on Wednesday, there is a lenses law question. It's not exactly like this, but it's the same kind of idea where, look, you're moving a magnet relative to a coil or a ring or something like this. You generate an electric current. That electric current generates a magnetic field, and you got to figure out something like you did here, the polarity or the direction of the current or something like that. Yeah. So be ready for that. Number 2. Probably should have started off with this one because this is the easier one for sure. This one's the one we got to nail, right? And you guys did. You guys did a good job on this. We got a negatively charged particle. It's going to mean it's a left-hand rule question. Got a magnetic field going from north to south. Wait a second. The last question, didn't we say the magnetic field went from south to north? Yeah, we did. So what's the deal with that, Colin? Good. Inside it's from south to north. Outside it's from north to south. So you got a particle going to the right through a magnetic field that's pointing toward the bottom of the page. Hey, what hand rule are we going to use here? Remember, we got 3 of them. We got the wire grasp rule. We got the coil rule. And then we got the deflection rule. Which one do you want to use? I think we're pretty clear on which one we're not going to use. Which one is the most obvious one that we're not going to use? Sorry? Now we're not going to use the wire grasp. I think the coil rule is the most obvious one there because we don't have a coil, right? You got to have a coil or a ring to use a coil rule. So we're not going to use that one. Not going to use the wire grasp rule either, even though this does generate its own magnetic field. And technically, if we wanted to find the magnetic field surrounding it, we could use the wire grasp rule. It's just we're not asked that. We're going to use the deflection rule here. Thumb in the direction of the particle towards the right, fingers from north to south, palm points outwards, out of the page. So the answer is going to be B. Another numeric response here. Hey, we look at a question like this. We have to nail this question, right? We have to get 100% on this question. We can't afford to have anybody get this question wrong. Okay, these are the questions that, look, they'll appear on your exam. They will appear on your diploma exam and on your unit test. But they're the ones that are designed to give you a fighting chance. Okay, there's going to be a lot of hard questions, a number of hard questions. And we're going to get some of those hard questions wrong, most likely. So if we want to do well, okay, and still get some of the hard questions wrong, which is okay, we can't get these ones wrong. What's the length of the wire? Well, we got F is equal to ILB. We just rearrange the equation, right? L is equal to F over IB. Look, we don't even have a unit conversion to do here. Most times you get a question like this, we're going to have centimeters or milliamps or something for my current. Okay, no conversions here to do at all. We do the math on this, it works out to be 6.24, I believe, wasn't it? Times 10 to the negative some. Now, they want it in scientific notation. This doesn't even say, this doesn't say A decimal B C times 10 to the D, or it doesn't say B times 10 to the negative W. It just says blank. How do you think they want me to express that? 6.24, 624 something, just 624, what is it? How do we fill that in? Yep, 6.24. It's the same thing as saying B times 10 to the negative W, right? Good. Now this bothered people. It bothers me a little bit too, to be honest. I don't like questions where they give us a new equation that we've never seen before, but it happens. I don't know that it'll happen on your diploma exam, but it does happen from time to time. I'm not a big fan of that, because to me, if they want you to know something, they should put it in the curriculum and tell us to teach it to you. But in the end, when they do that, it's not the end of the world, because they always explain it. They're not going to put an equation on there that you've seen before and explain it, but they might put one on there that you haven't seen before and then provide you with some information like they have right here. In the end, look, that's enough information that if you need to solve any question involving magnetic fields surrounding or inside a solenoid, you could do it. Let's see what they ask me. It's direction of conventional current in the solenoid in the direction of the shape of the magnetic field. Picking up my red pen here. Why? What's so important that I underline or circle or highlight in this question? Okay, there's something that's critical that I draw attention to. What is it, Mark? Yeah, it's conventional current. We don't see that very often. Not at all. Okay, I've told you guys that I've been through 39 diploma exams now in Physics 30. Okay, this will be my 40th, coming up on June 25th. And I bet I can count on one hand the number of times I've seen them use conventional current. It's not likely to happen for you guys. Okay, it's happened maybe, well, 1/8 of the time, 5/40ths of the time, 12% of the time. It's not common. But we have to be ready for it if we see it. Mark, what does conventional current mean? Right, it's the flow of positive charge. Now, that's not really how charge flows, because it's electrons that flow within a wire, right? Hey, but 150 years ago, when we didn't know about the structure of the atom, that there was even protons and neutrons and electrons existing, we just assumed that it was positive charge that flowed. We knew about charge, we knew about current, we just didn't know where it came from. So we assumed that it was positive charge that moved. And you know what? It worked. It worked. In 1897, we discovered the electron and start figuring out, wait a second, it's not protons, it's not positives that flow around a circuit, it's negatives that flow around a circuit. But the analysis that we did for the positives ended up giving us the same answers as the analysis we did for the negatives. So in the end, it didn't matter. Because of that, some people kept using conventional current, the flow of positive charge, in their analysis because it gave them the right answer. It still does. Even though we know that it's electrons that move, conventional current still works. So every once in a while, you still see somebody using conventional current. Mark, you're right. Okay, you said that it flows from positive to negative. That means that B and D can't be right. Forget about the coils. Okay, forget about the magnetic effect here. Let's just look at the current. In B and D, you've got electron current. Okay, electrons leaving the negative end, go around to the positive end. Wrong. Okay, it's got to leave the positive and go around to the negative end. So it leaves us with either A or C. Now, the only question between A and C now is, which one produces the magnetic field shown in the diagram? Well, let's use our coil rule to figure this out. In both cases, we have a current going to the right in the front. Let's figure out what the polarity of this is. Right hand, right? Because it's conventional current. Right hand, fingers toward the right side. Right fingers toward the right side in the front. Thumb points upwards. So the magnetic field inside points upwards. Which one's going to match up with that? A or C? It's going to be C, right? The magnetic field goes from north to south on the outside, goes from south to north on the inside. And number 4, that also goes with that information, but didn't really require that information. Which of the following unit combinations is equivalent to a unit Newton per amp squared for this term mu sub 0, this constant? I'll tell you what, I'm not a big fan of these questions, these unit questions, because to me it's kind of math as opposed to physics. But hey, it is what it is. If we see it on a test or exam, we got to deal with it, right? There's 2 ways of tackling this. I'm going to show you the way that I did it first, which gives you the correct answer. And then I'm going to show you the way that some people in the last class did it, which is probably for this question actually better than the way that I did it. But I want to expose you to both ways because there is a question on your test that you're going to have to do, and you're going to end up having to use my way for the question on the test. So let's look at my way first. We want to find out the unit combination that's equivalent to a Newton per amp squared. Basically, this has to turn into one of these. That means that we've got to look at a Newton per amp squared, and we've got to either replace a Newton with something, or an amp with something, or a Newton and an amp with something. Let's come up with some equations that will give us something else instead of a Newton, or something else instead of an amp. We know that F is equal to M times A. Okay, that'll give us a Newton is equal to a kilogram times a meter per second squared. We know that F is equal to QVB. We know that that'll give us a Newton is equal to a Coulomb times a meter per second times a Tesla. We know that F is equal to ILB. That'll give us a Newton is equal to an amp times a meter times a Tesla. And you know what? There's other equations for force, gravitational force, electric force, but they're completely out of the context of this question, right? This is a magnetic force question. So let's not introduce anything else there. For an amp, well, we know that I is equal to Q over T, or an amp is equal to a Coulomb per second. So lots of different combinations of units here that I can swap in for a Newton and an amp and see if I can get something here. Now, here's the thing. You can try any of them because they're all valid. Okay, there's one that I think is the most efficient one, and I want you to look at the 4 possibilities here to see if you can identify which one that is. Notice in 3 of these 4 possibilities, I see a Tesla. Notice in 3 of the 4 possibilities, I see an amp. Notice in 4 of the 4 possibilities, I see a meter. So Tesla, amps, and meters seem to be the big units in all of the possibilities, right? Which one do you want to start off with? Yeah, let's start off with the third one. You don't have to. You can make this work even if you don't start off with the third one. But if I've got these 3 units as being overwhelmingly in my possibilities, that's the one I think I want to try first. So let's do that. Let's say that a Newton per amp squared would be equal to an amp times a meter times a Tesla over an amp squared. Do we see that anywhere? No, we don't, but we can simplify this. Cross off an amp. Do we see that anywhere? Yeah, it's option A, right? Done. Got it? Now, let's say you had to start it off with this one. Okay, Cole noticed exactly what I noticed, okay, but let's say that he didn't notice that. Let's say he started off with this one. So we got a Newton per amp squared. We replaced a Newton with a Coulomb times a meter per second times a Tesla over an amp. Do we see that anywhere? No, we don't. Let's simplify it a little bit. A Coulomb per second is an amp. One of the amps cancel, and lo and behold, I get the same thing, right? Make sense, guys? How many people did it more or less like that, using that kind of idea? Yeah? All right. That's what you're going to have to do on Wednesday's test. Got it? Now, the method I'm about to show you works really well for this question, but it doesn't work really well for all questions where you're trying to do a unit analysis. Okay, in this question, they give you a little bit more. They give you this equation. Okay. We know this mu sub 0 is Newton per amp squared. If we rearrange this equation to solve for mu sub 0, we end up getting 2 times L times B over N times I. And there's no units for the 2, meters for the L, Tesla for B, no units for the N, amps for I, and would you look at that? Meters times Tesla over amps, that's option A. Got it? How many people did it that way? Okay, not very many, actually. Quite a few in the other class did. And you know what I told them? You can't do that on the question that's on Wednesday's test because you don't have the equation that goes with it. But that's okay. If you can find what I think actually for this question is a better way than what I did, then go ahead and use it. Absolutely. Just be prepared to be able to do it the other way too, that's all. All right. Here's another Lenz's law thing. The apparatus illustrated below, coil 1 is suspended by an insulating thread such that the coil can swing freely. Coil 2 is connected to a DC power supply. So here's what's happening, guys. You got a coil down here, coil 2, that's got an electric current because it's got a battery. The current is going to go counterclockwise, up in the back, down in the front, like this. It becomes a magnet. It becomes an electromagnet with a certain polarity, a north and a south pole. As we move this magnet, we can redraw this if we want. Pretend it's just a bar magnet. We just have to figure out its polarity, that's all. As we move it towards coil 1, which is not attached to a battery, what's going to happen? Well, remember early on in the unit, Oersted said a current produces a magnetic field. Thursday, Faraday said a magnetic field produces an electric current if you move either the wire or the magnet. And then on Thursday, Lenz also said that, oh, look, a magnetic field produces a current, but that current produces another magnetic field, and those two magnetic fields oppose the motion. All right, let's figure out what the polarity of coil 2 is, and then figure out what we have to do for X and Y here, okay? So once again, here's our coil. Guys, it's okay on Wednesday's test to take a piece of paper and roll it up and turn it into a coil. Okay? It's okay. Like, do what you got to do. We got current pointing down in the front. Thumb points toward the left side, right? That means this is going to be north, and this is going to be south, because the magnetic field inside points from south to north. If I move a magnet, pretend it's just a plain straight bar magnet. If I move it to the left, what does Y have to become? There's a polarity induced in Y because there's a current produced in that coil, which produces the magnetic field. But what pole does Y have to become, north or south? Yep. Has to become north because it has to oppose this motion. And the only way to oppose that motion is to make it the like pole. All right. If that becomes north and that becomes south, well then, we know the answer either has to be A or B, right? Because then Y has to be a north pole. Is it going to move towards it or is it going to move away from it? Well, if coil 2, its motion is opposed, it's pushed to the right by Newton's third law. The other one has to be pushed to the left, away from it, right? If it's a repulsive force on one of them, it's got to be a repulsive force on both of them. Object A applies a force on B, B applies a force on object A. So it's going to be A here. Swings away from coil 2. How many people got that one? Good. Now, I'm gonna have you guys learn from what I thought was a great question from somebody in the last class. Person said, how do we know when to do Lenz's law versus just, look, you got a magnet nearby, like a piece of steel, and you're causing a temporary alignment of the domains, right? Shouldn't it attract? Shouldn't they attract in that case, right? Okay, we said that very first day of the unit. Hey, you got a piece of steel right here. Okay, it's not magnetized. Domains pointed every which way. You bring another magnet nearby. Isn't that going to align the domains like this? So that the two are going to attract each other? The answer is yes. So how do we know which one we're dealing with? How do we know whether it's going to be like poles, like we did right here, or opposite poles, like we did on the first day of the unit? Yep. Yes. Yeah. The fact that coil 2 is a coil is irrelevant. Okay, that was a plain bar magnet. That would be fine. Same analysis here. What's important is this one. If that's just this, okay, then bringing that nearby would cause attraction. But it isn't just that. We've got wire wrapped around it. And as soon as you got wire wrapped around it, you produce a current in that wire. Okay, that's the fundamental difference. There's no current here. This is just making a magnet. Separation, or sorry, a temporary alignment of domains. Here you're generating a current, and that current is what magnetizes the thing inside. You got a wire wrapped around it. Let's go with coil rule and Lenz's law. If there's not, then let's go with what we learned on the first day of the unit. All right, almost done here, guys. Almost done this part, anyways. 6. Hey, you got an electron current going clockwise here. Which way is the magnetic field? Okay, wire grasp rule, right? Thumb in the direction of the current. Fingers kind of get wrapped around it a little bit. Towards the right of it, it's going to be into the page. Answer is going to be A. 7. Charged particles moving towards Earth, trapped within a field near the Earth, where they cause the northern lights and the southern lights. The field in which the particles are trapped is, I kind of laugh when I see options like B. An induction field? What? What? Those answers are the answers where, they're going through this, they like the question, they're like, geez, I just can't think of a fourth possibility. Let's make one up. Induction field. People will guess that one. And you know what? It's funny because people sometimes do guess the one that they've never heard of before. Say, oh, I've never heard of it before. It must be the answer. Guys, do you see the logic in that? I've never heard of it before, so it must be the answer. Maybe if you've never heard of it before, it can't be the answer. The answer is going to end up being C, the magnetic field caused by the Earth. And finally, so we got these maglev trains. We're repelling the train, basically, pushing the train upwards so that it's not making physical contact with a track, and therefore no friction, basically. You got a little bit of air friction, but that's it. It makes it way more efficient and allows these trains to travel maybe even 500 kilometers an hour. Like, we're talking high-speed trains here. So the question is, which of the following designs would produce the greatest lift? This is not a Lenz's law question. Okay, understand the difference here. Okay, it's not a Lenz's law question because the ones with coils all have a battery attached. Okay, Lenz's law involves coils or rings of conductors with no battery attached. Those are the ones where you're trying to generate the current in the coil, not you got a current already because you got a battery. This is not Lenz's law. This is just look, we got a battery attached to a coil. What's the polarity? And then which one's going to repel best? So let's look at it. Okay, all four are set up in more or less the same way, where you got a current going counterclockwise to the right in the front and to the left in the back. Left hand, fingers to the right in the front, thumb points downward. That means in all four cases, this is going to be north, this is going to be south. Okay, let's eliminate 2 right now. Which 2 cannot possibly produce the greatest lift? And in fact, which 2 cannot possibly produce any lift? Cool? Why would it be C and B? A and C, yes. A and C can't produce any lift because north is attracting south, right? That's going to pull the train down, right? Now, there is one form of maglev train that actually uses attraction, okay? But it's set up completely differently. It's not pushing the train up. It's pulling the train down, but it's a completely different design, okay? Now, if you were to see that on a test or an exam, okay, I'm not suggesting it's going to be on Wednesday's test by any means, okay? But if you were to see something like that sometime, don't remember that maglev trains repel. I mean, look at the picture and see whether it needs to attract or repel. Okay, in this case, clearly it needs to repel. So it's got to be either B or D. All right, so they both produce repulsive forces. Which one's going to produce the biggest repulsive force? Yep, D. Yeah, good, more coils. Now, I asked that same question at period 1. I said, why does D produce the biggest force? And somebody said, oh, because it's got more current. Does it have more current? Looks like the same battery. It's probably going to be the same current, right? So why does it produce more force? Not because it has more current, Josh, because there's more coils. And more turns of wire in the coil generates a stronger magnetic field. Not a stronger current, but a stronger magnetic field. Okay? Basically, it's a longer length of wire, right? Is that okay?